Okay, that was fast 2 minutes. The next talk is going to be on DC to DC converters.
Okay. Does it work with this? Because I'm not sure.
By Zoe Böhle.
I have this.
She's an enthusiast for open hardware and fan of DIY, and has been working on the topic of DC to DC converters for a long time.
And I'll get to work.
And I have to keep on talking now because it seems that her computer is not really communicating with the presentation device. We do have a picture, but we don't get it moving.
Come back and ask you. Okay, I'm gonna. Because this can work. This is working. Okay, this one's working. From this distance. Okay. Yeah, that's.
While we're still having some issues up here, I might remind you that it is very helpful if you take your trash with you. And now please welcome Zoe, and we are ready to roll. Give her a warm hand.
Hi. My name is Zoe, and this is the first time I'm standing here on a Chaos stage, so I'm a little bit anxious, but I'm here to talk to you. I'm here to talk about DC-DC converters, and the talk's called DC-DC converters and everything you wanted to know about them, but it's unlikely I can fit everything into a 50-minute talk, so it's not everything. But my goal is to provide you some starting points and give you an overview. And hopefully, if you already worked with DC-DCs, then you're also not gonna be annoyed and not gonna be bored. So, before I start with the DC-DC topic, I would like to ask you to be excellent to each other, and this is not related to my talk, but I hear people starting clapping when someone breaks a bottle accidentally, and I think that's super not cool. So yesterday I saw someone breaking down in tears because they just broke a bottle and everybody was clapping and paying attention to them, and that was like harassment. So please don't be the one who starts clapping. But also, I'm not here to forbid you to clap, and just know what's happening. So, brief introduction to DC-DCs and why. Quite often, you need different voltages than what you have available. For example, you have a microcontroller, or you have an FPGA and you work with a battery, then you need to provide a different voltage for that circuit. And the trivial solution is to just use two resistors and make a voltage divider, but this is totally unsuited for power delivery, because as you start loading the output voltage starts dropping. Also, this circuit dissipates power even if there is no useful load on the output. So this is only useful for signals, and to have some kind of feedback and regulate the output to a desired level, you can use an LDO, which is the same thing, but you control one resistor, very simplified, to always keep a desired output voltage. Of course, this can only go lower than your input, and your efficiency is limited to the ratio of the output voltage and the input voltage. And this is even an ideal situation. So instead of burning up power in your converter, you can just use switches. And this is the idea behind switching supplies, that you use a switch element which is either fully on or fully off. And if it's fully on, then there is no loss on the switch. And if it's fully off, there is no current flowing through it, so there is no loss either. There are some practical problems with this approach, but this works for LEDs and heaters if your switching frequency is high enough. To think of a DC-DC converter is a box with 4 terminals. It has an input side and an output side. And right now I'm talking about buck step-down DC-DC converters, which are non-isolated. This means the ground in the input side and the ground on the output side are connected together inside. And this limits certain uses. Also, you should not connect these DC-DC converters in series. So if you have a block like this and you think, oh, I could use 2 or 3 of them and just connect them in series to deal with higher input voltages, that's going to blow up very quickly. A block looks like this on a screen and might look like this in reality. And let's take a look inside. So all of these DC-DC converters consist of a power stage, a control system, and a feedback. And the feedback is there to provide a regulated output regardless of the operating conditions. So what's inside a power stage? To have a deeper look inside, we can consider this asynchronous buck converter, where a switching element, a MOSFET, is controlled by an analog and digital circuitry. Feedback is provided from the output voltage, and we see a diode in the middle, which I'm going to talk about soon. You also see 2 capacitors on the input side and on the output side, which are also very important. More about them later. Let's consider the first situation. The switch is on. This is so-called the on state. And this forms a loop from the input to the output. So the input capacitor we can neglect, and in an ideal situation, the output capacitor is I will talk more about the output later. All right, I don't want to make this into a lecture and everybody's sleeping in, and the fun part will start very soon. So this DC-DC has 2 states. Either the switch is on or the switch is off. Right now the switch is on, and you see that the current can flow from the input through this inductor to the output. The inductor resists the change of current. It's like pushing a heavy mass, and once it starts moving, it wants to keep moving. That's why in this on state, the input current flows through the inductor and starts to increase while it's also flowing to the output. Then the converter turns the switch off, which comes to the off state, and now the diode comes into play, which will keep the current recirculating. In this off state, there is no current from the source to the output, but the output is still powered from this decaying magnetic field through the inductor. And sometimes you hear about synchronous DC-DC converters where this diode is replaced by another switch. In that case, efficiency is increased since the voltage drop across MOSFET is lower than the forward voltage of the diode. So in this case, as you can see, current is still being delivered to the output. And this is the big advantage of the buck converter, that in both in on and both in off states, the output is sourced with current. And so what the output capacitor does there is it provides the difference between the inductor current on the lower end. You can see the inductor current as the switch is on, it ramps up, and the switch is off, it ramps down. And in the middle, you see this line, which is the output current. So you see these triangles, and this is what's provided by the output capacitor. All right, so this is an actual part without the simplifications. And I would like to talk a bit about the reference voltage and how that works. So this device creates an internal 0.7 volt reference. And you can program the output voltage by choosing R1 and R2 on the left side. So at your desired output, exactly 0.7 volt will be at this voltage divider. And this converter will keep regulating to reach the state. There is, if you're looking for a DC-DC converter to your next project, then you might see a bunch of parameters, and I'm going to talk about those. So first, you see a 3.3 volt 2 amp converter. What does it mean? This depends on how and who specifies that output, because someone says it's 2 amps if it can provide 2 amps for a second, and someone says it's 2 amps if it can continuously provide the 2 amps even in a warm environment. So it's important to talk about if it's peak or continuous current rating. Then there is this so-called output ripple. You saw that switching action going on and off, and that will create a ripple on the output voltage. So it won't be 3.3 volt, it will be oscillating around that. This can be as low as a few microvolts and as high as a few volts, depending on the parameters. Also, there is voltage accuracy. So maybe it's labeled as 3.3 volts, but actually it's 3.5 or 3.0. Load regulation. It's maybe 3.3 volts when it's unloaded, and as you increase the output, it starts changing the output voltage. There is a line regulation, which means the input voltage has influence over the output, which is undesired. Then there is this maximum input voltage rating. Let's say this converter can tolerate 7 volts on its input. So you think, oh, let's just hook it up to USB. That's 5 volts, right? Yes, but no. Because when you use cables and non-ideal conditions, you can create transients which overshoot the voltage possibly way above this maximum rating. And this can lead to very nasty surprises, because sometimes they fail short, which means they connect their input directly to their output. In this case, the device you connected to the converter might also go up in flames. So mind the transients, and always have some margin between your desired input voltage and the maximum the converter can tolerate. Then you might see 95% efficiency, and let's also question at which load, because at maximum specified load it will be lower, and at less load it will be also lower. So there is this efficiency peak what marketing people love to specify. There's also this so-called quiescent current, which means your converter draws current from your input even when there is nothing on its output. And if it runs from a battery, this can drain your battery in days or weeks. So you must pay attention to this. And there is this other factor called switching frequency. So how fast, how often the internal switch changes state. But this might not be a constant value, especially with the previously mentioned quiescent current feature. The converters that excel at having a low quiescent current don't have fixed switching frequency. So you might have noise at different frequency bands and disturb your circuits or radio noise. Let's talk about a few features you might want to look for. Enable functionality. This is very useful to easily disable your DC-DC converter and without having to interrupt either the input side or the output side. Let's say you have a 20 amp output converter. You really don't want to switch the 20 amp with a mechanical big switch. And instead of that, you have a logic input to your DC-DC converter with which you can turn this completely off. Then there is a so-called undervoltage lockout. You might want to prevent it from running below a certain input voltage to prevent draining your battery too deep and turning it completely off. There is this power good that can provide information to your processor that the output voltage is in regulation and stabilized. So if you hook up the power good output to, let's say, a reset line or enable, then you can be sure that the output voltage is already stable and it's not going to go, your processor not going to go into glitch. Over temperature shutdown is very common these days, and that makes these tiny converters almost indestructible, because if they get too hot, they just turn off completely before they get permanently damaged. Efficient standby, this is the so-called low quiescent current option. That means if your output is off, your processor is sleeping, then it will reduce switching action to reduce switching losses and might only draw a few microamps or even nanoamps. Very important for battery-powered applications. Then you might see overcurrent protection, which makes the output very robust. You can even make a short circuit, and the overcurrent protection will limit the output current to this value. And this prevents damaging of the converter and also damages to the cables and switches if they are rated to withstand the overcurrent protection limit. And let's talk about noise. The output ripple is not exactly noise. Output ripple is there because the output capacitor is non-ideal, and usually this is very low on a properly designed converter. But if you measure the output, you might see spikes on the output, and that's not a ripple, that's conducted EMI. Because on that inductor, the windings are coupled very closely. There is some capacitive coupling between the wires. So the digital on-off action from the switches will propagate to some extent to the output. And this is attenuated by the capacitors, but they cannot be completely filtered off. And you will see the switching frequency and even upper harmonics of it. But this can also be filtered. And there is also radiated EMI, which comes mostly from the switching node and capacitive coupling to the ground plane. And also the inductor, if it's not shielded, then a magnetic field can also radiate out and cause interference. On this picture, what you see is that gray block. That's a shielded inductor, and the two blue connectors at the end of this PCB are screw terminals. And I personally advise against using this style of screw terminals because the wires can easily slip out, make a short, or you don't notice that they're not connected. So I prefer a different style of connectors. Okay, so it's good to know about non-ideal components. The capacitors that are used have a so-called DC bias. These ceramic capacitors, multi-layer ceramic capacitors, are very sensitive to the DC voltage across the terminals. And if they are rated, let's say, 20 microfarads, at their rated voltage, they might lose up to 90% of their capacity. So you always have to pick a capacitor that's rated to a higher voltage than what your output is to compensate for this effect. And you also need to put more capacitors at your output as what you would think in an ideal situation. Mind the transients. As I said, if you plan to hot plug, connect to live wires, your converter, you have to keep in mind the inrush current. Those capacitors, when they are fully discharged, and you connect that to the input, then they will try to charge to the input voltage as fast as the cabling lets that happen. And the cables have inductance, which will store energy and overshoot the input voltage. When fiddling with MOSFETs, don't forget the ESD protection. And MOSFETs are very sensitive at their gate because the oxide layer is so thin that even 20 volt voltage is enough to break it down. And a 20 volt ESD strike is something you probably don't even notice, but it can damage the MOSFETs. And avoid the 7800 series LDO because that's a very old part, and I still see it in new designs, while there are much better ones with better regulation, less quiescent current, and that's also an LDO. So it's like just marginally related to DC-DCs. If you make your own DC-DC converters instead of buying one, you should read the datasheet and follow the instructions, because the manufacturers give you a proven, tested layout